Hello students, let us proceed with the continuation concept of Unit 2, boundary conditions. Boundary conditions are defined in terms of two set of fields. One is electric field, other one is magnetic field. As we are in the progress of second unit, we are going to learn the electric field boundary conditions. As the term itself defines, it is a boundary. We have come across this term frequently in the cricket field. So far, existence of electric field in homogeneous medium is discussed. In unit 1 I am speaking about. Now, if the field is existing in a region consisting of two different media, then the boundary conditions are defined at its interface. What are the possibilities of defining the boundary conditions? They can be defined at conductor-free space. We know what is a conductor, what is a free space, what is dielectric. So conductor-free space is one condition. Conductor dielectric is second condition. Different dielectrics, dielectric 1, dielectric 2. But what is the basic difference between these two equations A and B? I mean the two conditions. The two conditions are one and the same with a simple difference. For free space we will substitute epsilon r equal to 1. But for dielectric we will have epsilon naught epsilon r. That is a simple difference. Conductor medium remains the same in both cases A and B. Free space dielectric, in case of free space, epsilon equal to epsilon naught epsilon r is modified as epsilon equal to epsilon naught. But in dielectric it is epsilon naught epsilon r. That is what? Epsilon equal to epsilon naught epsilon r in B. In A it is epsilon equal to epsilon naught. Now, we will move on to the analysis of what are the governing equations. With the analysis of the previous unit, what we have learnt so far, I am choosing three set of equations. Integral closed path, that is E dot dl equal to 0. This is condition number 1. Second condition is a familiar equation, Gauss law. The surface integration of D is equal to the charge enclosed. Integral D dot ds is equal to charge enclosed. Third condition, E and D, electric field intensity and the electric flux density, can be viewed as the composition of tangential component and the normal component. Mathematically defined as E equal to E tan plus E normal, D equal to D tan plus D normal. Now, we will go into the first media, conductor free space condition. So, this is the boundary existing between the conductor and the free space. So, this is medium 1, this is medium 2. Let me assume the medium 1 to be free space, medium 2 to be the conductor. A very important concept is inside the conductor, electric field intensity E is equal to 0. This is very, very important. This is inside the conductor. So, this portion inside the conductor, electric field intensity E is equal to 0. So, I am choosing two set in the diagram. As I told you, I have drawn a boundary between medium 1, medium 2. Medium 1 is free space, medium 2 is conductor. A closed line path A, B, C, D is chosen. A pillbox. In the medical shop, you would have got the tablets in the pillbox representation. So, this pillbox representation for surface analysis. Two conditions we are going to discuss about. In this closed line path, let me define this to be del H and this to be del W, width to be. Again, I am choosing a point at the surface to be B dash, D dash. So, with the analysis, we are going to proceed with the derivation. How to proceed with the derivation? Okay. Now, tangential component, normal component we are going to calculate. First, we will calculate the tangential component. As spoken, governing law 1 is integral E dot dl equal to 0, which is defined theoretically as work done in moving the unit positive charge along the closed path is equal to 0. A known concept of unit 1 it is. So, integral E dot of dl is equal to 0 is applied for this closed line path. So, A to B, B to C, C to D, D to A. So, I am splitting this E dot dl as integral A to B E dot dl, integral B to C, integral C to D, D to A. Next condition. Again, choose a center point at the conducting surfaces. This is conducting medium, this is free space medium. It is meeting at the point of B dash, D dash. So, B to C is divided as B to B dash to C. D to A is divided as D to D dash to A. That's what I have written very clearly in the mathematical equation. B to C is divided as B to B dash to C. Same way D to A as D dash to A, D to D dash. Now for the path of which all the paths inside the conductor. Now come back to the diagram. B dash to C, C to D, D to D dash. All these three paths are inside the conductor. So inside the conductor E is equal to 0. So when I choose a equation, integral A to B E dot dl remains the same. B to C I have split as B to B dash to C. Again C to D is lying inside the conductor. D to D dash to A. So these three are lying inside the conductor. So E is equal to 0 inside the conducting medium is very clear in the equation. So when these are cancelled out, we are left out with what equations? Integral A to B E dot dl, integral B to B dash E dot dl, D dash to A. Again come to the diagram. How to find out integral A to B E dot dl? So the E value moving parallelly along this is E tan. So E tan 1. Integral dl is nothing but equal to del W. So integral A to B E dot dl is written as E tan of del W. Likewise, I have to find out B to B dash. When I find out B to B dash, it is very clear in the diagram that it is a normal component. So when it is a normal, B to B dash is a normal component. But this is moving inward, this is moving outward. So it is minus of. So the second term is written as E normal del H by 2. Same way, when it is in the opposite direction, it is minus of del H by 2. So we have the analysis of this value E tan of del W. This is E n of del H by 2. This is E n of del H by 2. All these both are in the opposite directions. So we have the analysis to be very clear that these two are cancelled out. We are left out with E tan of del W equal to 0. This is a product term. Mathematically, we have defined some del W value. So the line has been defined with some width. So del W cannot be equal to 0. So automatically E tan becomes equal to 0. But by consecutive relation, we know that D is equal to epsilon into E. So D tan is equal to epsilon into E tan. As E tan is equal to 0, D tan is also equal to 0. First set of equation is arrived at. So E tan equal to 0, D tan equal to 0 or the tangential components. Now we'll move on to the normal components. For which case I have to consider the pillbox representation. So this is a surface. This surface is del S. This is the normal component. Again this is a tangential component. This is D value. Now with this, let us choose the Gauss law, second governing equation. Integral D dot D is equal to charge enclosed. Now in the diagram it is very clear. Integral D dot ds is defined for top surface, bottom surface, left side surface, right side surface. Be clear with. So 4 surfaces I have written here. So top, bottom, side surface inside the conductor, side surface in the free space. So as we already know, this bottom surface is purely lying inside the conductor. So inside the conductor E is equal to 0. Likewise, 1/2 of the side faces is lying inside the conductor, whereas the other part is also a very small value which can be neglected. So the other part also becomes equal to 0. So we are assuming that bottom face and the side surface in the conductor and free space to be equal to 0. We are left out only with the integral of top surface alone. Now, what is this integral ds? In the diagram you can see very clearly we have chosen the surface area to be equal to del S. So I can write the equation integral ds to be equal to del S. The surface charge density is rho S. So with this analysis we write the normal component of D to be equal to dn. So Q enclosed becomes equal to rho S del S. By definition, integral D dot ds with respect to top surface alone we are considering. So it is dn of del S equal to rho S of del S. It is a surface charge density. Integral ds is del S already we have seen. So del S cancels out. We are left out with dn equal to rho S. By consecutive relation, d equal to epsilon into E. So dn becomes equal to epsilon naught epsilon r of En. Therefore, En becomes equal to dn divided by epsilon naught. For free space epsilon r is equal to 1 is a known condition. So En becomes equal to rho s divided by epsilon naught. So dn equal to rho s, En equal to rho s divided by epsilon naught are the normal components. So we have calculated the tangential component, normal component for conductor free space. For conductor dielectric, same equation holds, but in the place of epsilon naught we will also include epsilon r. That is a simple difference, as in the first AB itself we have discussed about. The third part of the analysis of this derivation is dielectric 1, dielectric 2. A simple difference. Here no more conducting medium, so nothing is going to be equal to 0. So we will see the diagram as such. Let me define dielectric 1 to be with epsilon 1 equal to epsilon naught of epsilon r1, and dielectric 2 to be with epsilon 2 with epsilon naught of epsilon r2, which means that epsilon 1 becomes equal to epsilon r1, epsilon naught 2 is defined in terms of epsilon r2. Now one more assumption we are doing, that there are no free charges on the boundary surface between dielectric 1 and dielectric 2. This is a main assumption. Same diagram we have drawn with a simple difference that there is no conducting medium. This is dielectric medium 1, dielectric medium 2, epsilon r1, epsilon r2. So I have the same surface analysis with for pillbox, the closed line path A, B, C, D with del W, del H, but there are no pointing B dash, D dash. So everything is existing. So let me consider for the tangential component A, B, C, D, A. This is a closed path, line path. Again it is A to B, B to C, C to D, D to A equal to 0. Now what is the equation for A to B? A to B it is E tan 1. So E tan 1, del W is DL value. Next condition, this is E normal, it is inward. So minus En of, this is del H value, overall value is del H. Again this is flowing in the opposite direction. So it is E tan 2 of same del W, again in the opposite direction, so plus En of del H. Remember, these horizontal components define ET with respect to medium 1, medium 2. Likewise, these are the normal components, En1, En2, which is both are equal. So it is chosen as En. So En inward, En outward. When it is inward it is minus, and when it is outward it is plus. So both are cancelled out. We are left out with the equation del W is common, E tan 1 minus E tan 2 equal to 0. But mathematically del W cannot be equal to 0. We have defined the width of the line path. So del W cannot be equal to 0. Automatically Et1 minus Et2 becomes equal to 0. So E tan 1 equal to E tan 2. By consecutive relation we know dt1 equal to epsilon 1 Et1, dt2 equal to epsilon 2 Et2. Here we have analysis very clear, as Et1 equal to Et2 I cancel out these two, and dq1 divided by dt2 ratio is nothing but equal to epsilon r1 divided by epsilon r2. This gets analysis of the tangential component of dielectric 1, dielectric 2. The continuation concept is a normal component of dielectric 1, dielectric 2. Same analysis. Choose the Gauss law. Integral d dot ds is equal to charge enclosed. So what we are doing is, we are writing top surface, bottom surface and the side surfaces. Now at the boundary, we are assuming that the area of the side surfaces are negligibly small, and so we are totally neglecting the side surfaces. We are considering only the top surface and the bottom surface to be equal to Q enclosed. As spoken, it is equal to Q enclosed is replaced by, in the previous analysis itself we have seen this clearly, Q enclosed is replaced by rho s del S, but your analysis of top face is dn1 of, in the diagram you have very clearly marked, this is dn1, it is projected outward, so dn1 of del S. This is again in the analysis of dn2, it is projecting inward into this, outward, inward. So dn1 del S minus dn2 del S equal to rho s of del S. Upon cancellation, dn1 minus dn2 equal to rho s. But what is existing at the two different media for a dielectric? It means that the surface charge density is equal to 0. So dn1 minus dn2 becomes equal to 0. Therefore dn1 equal to dn2 is a basic equation of normal component of dielectric 1, dielectric 2. Using the consecutive relation epsilon 1 en1 equal to epsilon 2 en2, I can write the ratio of en1 by en2 equal to epsilon 2 by epsilon 1, which means that en1 divided by en2 is equal to epsilon r2 divided by epsilon r1. So there are 4 set of conditions derived with respect to electric field. One is conductor-free space, for which I am finding the tangential component, normal component. Same way, dielectric 1, dielectric 2, for which case I am finding out the tangential component, normal component. This gets a complete analysis of the boundary condition. Thank you.